Okay, so the question here is to solve for y of x. Now we've got y double prime plus k squared y plus cosine of x equals 0. That's the information that we're given, and we're told that k is an integer, hence k squared is going to be larger than 0. So this here is a second order linear differential equation, because the y double prime, that makes it second order. So how are we going to solve this? Well, first of all, when we've got it in this form, we've got a cosine x, a y and a y double prime. Our x is our independent variable and our y is a function of x. So the y is dependent on x. So what we can do is we can set ourselves up to say our solution y of x will be made up of two parts. It'll be made up of a homogeneous solution for x and a particular solution for x. Okay, now the homogeneous solution is when we're going to set this to 0. But before we start, there's a little bit of a tidy up we need to do, because we need the y on one side and the cosine of x, which is our independent variable, on the other side. So we're just going to rewrite this: y double prime plus k squared y equals minus cosine of x. So for our homogeneous version of the answer, what we're going to do is our yh of x, we're going to find that by setting this to 0. So we'll have y double prime plus k squared y equals 0. So this is the first stage. Now the particular solution, we're going to need this minus cosine x in our calculations. So here we've got y double prime plus k squared y equals 0. Now separation of variables and integration is not going to give us the solution that we're going to need. So what we can do is we can use something called the characteristic equation. So the characteristic equation, I'm just going to write EQ for short. Now what that does, it works on how many derivatives y is taken as. So here we've got y double prime, so we'll write this as r squared. Now 2 is for the second derivative, so that's why we write r squared, and we substitute the y for the r. Here we've got k squared. Now our y here is not a derivative, it's just a function of y. So effectively we've got r to the 0, and that equals 0. Okay, now we know r to the 0 is just going to be 1. So that's just going to leave us with r squared plus k squared equals 0. Now for the characteristic equation, we need to solve for r. So bring the k squared to the other side. So r squared equals minus k squared. So now we take the square root on both sides. And that's going to leave us, well, r squared, take the square root, that just leaves us with r, which is what we want. Now here, we know that k squared is greater than 0. That's not going to be less than 0. So we know that this is actually a minus value inside the radical. So the minus k squared is going to leave us with plus or minus I times k. That's going to be our solution for this. So that's going to give us two solutions of complex value. So we have two solutions of complex value. So now that's going to set us up now how we can write our building blocks for our solution. So we now say that yh of x equals, now for the solution here we're going to set up some constants and some cosine and sine. So we'll have a cosine of x, and the x here we'll also need the constant k putting in, so x k, and then we add b sine, and then the value will be the same, xk, the input. Okay, so that's our homogeneous solution using the characteristic equation. So right here now, I'm going to put this on this side. A cosine of xk plus b sine of xk. Okay, that's our homogeneous solution taken care of. So let's take this off the board now, and now let's look for our particular solution. Okay, so now I've got my homogeneous solution. I need to find my particular solution. So let's just write this up here. So this is what we're looking for now. Now my homogeneous solution takes this form, but I need a particular solution format that is similar to this. So I'm not going to use the same constants, and I'm not going to use the same input. So my y of x in my particular solution is going to be in the form of something like c cosine of x plus d sine of x. That's somehow my format for my particular solution. So now I can look at what I'm trying to solve for my particular solution. So this time I need to include the minus cosine of x. So before I can proceed, I need to take the second derivative of my particular solution for x. So my y double prime p of x, basically I need to take the second derivative of this. Now my second derivative of this is going to be cosine derivative twice and my sine derivative twice. Well, we know cosine will become minus cosine and sine will become minus sine. So this just becomes minus c cosine of x minus d sine of x. Okay, so now I'm ready to plug that into my equation we first started with. So y double prime of p takes this form. So we've got minus c cosine of x minus d sine of x, and now I've got to add k squared y. So we reintroduce our constant term here. So our k squared we just plug in like that, and then our y we're going to plug in this value. So now we've got c cosine of x plus d sine of x, and that's set equal to minus cosine of x. Okay, so this is looking a little bit messy here, not a lot I can do there at the moment, but what I could do is I could get my sines and my cosines together and see what I can do from there. So start with the cosine. So if I do cosine of x and then take my constants which are before it, I've got a k squared c here and a minus c here. So I'm going to do k squared c minus c. And now looking at the sine, so I do add sine of x, and then factoring out for the sine constants, I've got a k squared d, and here I've got a minus d. So now I've got k squared d minus d, and that equals minus cosine of x. Okay, well, I can see cosine of x here is matching on this sine, but there's no sine here. So here I could write on here plus 0 sine of x. So I know here that this k squared d minus d equals 0. So I'm just going to follow down here. K squared d minus d equals 0 because there is no sine of x on the right hand side of the equation, although I've got one here on the left hand side. So then that's going to give me k, so if I factor out the d k squared minus 1 equals 0. So for that to equal 0, I've got my k squared equals 1 or d equals 0. That's the only way that this is going to be 0 on this side. Well, my k squared equals 1. Well, k could be any value, it's an integer. So therefore my d must be 0. Okay, let's do the same on this side. So here I've got cosine k squared c minus c. So how many cosines on this side must equal the number of cosines on this side? So my cosines on this side, I've basically got a minus 1 cosine of x. So k squared c minus c must equal minus 1. So k squared c minus c equals minus 1. So now, as we did with this side, I'm going to factor out the c. So now I've got c k squared minus 1 equals minus 1. And now I can get c on its own. So now c equals minus 1 over k squared minus 1. And here we've got k squared equals 1. This cannot be allowed because k squared minus 1 here will give us a function here that we're not allowed. It's undefined. So therefore k squared does not equal 1. So we can include that onto our conditions here. K squared does not equal 1. So therefore k does not equal plus or minus 1. Okay, so now we've got c here. Now our function here is y particular solution is y equals c times cosine of x plus d sine of x. So therefore we say our yp of x equals c, which is minus 1 over k squared minus 1 times cosine of x plus d, which is 0, but I'm just going to write it in anyway, z sine of x. Okay, so now that's going to give me my particular solution. I'm just going to take this off the board here and write that underneath here. So I'm going to write that here. So y p of x equals minus cosine of x over k squared minus 1. Okay, let's take this off the board, and now we can write down our solution for our second order linear differential equation. We'll say that y of x, working on this, our homogeneous is a cosine xk plus b sine xk minus cosine of x over k squared over 1 minus 1. And that's the conditions for this to be valid. So that is the answer to our second order linear differential equation. Okay.